Tonight, we're going to explore something that breaks every rule you think you know about how the universe works. Imagine grabbing hold of something tiny, something buried deep inside an atom, and trying to pull it out. With every other force in nature, the farther you pull two things apart, the weaker the attraction between them becomes. Magnets get weaker with distance. Gravity gets weaker with distance. But there is one force in the universe that does the exact opposite. The harder you pull, the stronger it pulls back. And if you keep pulling, if you put in enough energy to rip the thing free, the universe does something astonishing. It uses that energy to create entirely new matter, rather than ever letting a single quark escape alone. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, but probably haven't thought about deeply enough. You are made of atoms. Everything you can see, everything you can touch, everything around you right now, the screen you're watching this on, the chair you're sitting in, the air you're breathing, all of it is made of atoms. And inside every one of those atoms, there is a nucleus. That nucleus is incredibly small. If an atom were the size of a football stadium, the nucleus would be a tiny marble sitting at the center of the field. But here is what most people don't realize. Almost all the mass of that atom, more than 99% of it, is packed into that marble-sized nucleus. The electrons orbiting around it contribute almost nothing to the atom's weight. So the mass of everything you see is really coming from the nucleus. And that nucleus is made of protons and neutrons. You probably learned that in school. Protons carry a positive electric charge. Neutrons carry no charge at all. They sit together in the nucleus, packed incredibly tightly, forming the dense core of every atom in your body. A hydrogen atom has one proton. A helium atom has 2 protons and 2 neutrons. An iron atom has 26 protons and 30 neutrons. A uranium atom has 92 protons and 146 neutrons. Every element in the periodic table is defined by how many protons sit in its nucleus. But here is the question that changes everything. What are protons and neutrons made of? For a long time, physicists thought protons and neutrons were fundamental. They thought these particles were the bottom of the ladder, the smallest things that exist, the building blocks that aren't built from anything else. This seemed reasonable. Protons and neutrons behaved like solid, indivisible objects in every experiment people could run in the early 20th century. They had definite masses, definite charges, and definite properties. They seemed like the end of the line. But starting in the 1950s and accelerating through the 1960s, something strange began to happen. Physicists started smashing protons into each other at higher and higher energies using particle accelerators. These machines would take protons, accelerate them to nearly the speed of light, and slam them into targets or into each other. And when they did this, they didn't just see protons bouncing off each other. They saw showers of new particles coming out of the collisions. Hundreds of different particles. Particles nobody had predicted. Particles nobody had names for. The situation became chaotic. Every few months, somebody discovered another new particle. There were pions, kaons, sigma particles, lambda particles, delta particles, xi particles, omega particles. The list kept growing and growing. By the early 1960s, There were so many new particles being discovered that physicists were running out of Greek letters to name them. Enrico Fermi reportedly joked that if he had wanted to memorize the names of particles, he would have become a botanist. Willis Lamb, in his Nobel Prize acceptance speech in 1955, quipped that the discoverer of a new particle used to be rewarded with a Nobel Prize, but now such a discovery ought to be punished with a $10,000 fine. The situation had become absurd. Physicists called it the particle zoo because there were so many different species and nobody understood how they were all related. This was deeply unsettling. Science, when you find hundreds of different things that seem related but you can't explain why, it usually means you're missing a deeper layer. It usually means those hundreds of things aren't truly fundamental. They're made of something simpler, something more basic that combines in different ways to produce all the variety you're seeing. Think of the periodic table. Before we understood atoms, there were over 60 known elements in the 1860s, and the number kept growing. It seemed chaotic, but then we discovered that all those elements were just different arrangements of the same three particles: protons, neutrons, and electrons. Different combinations of the same basic ingredients produced all the variety. The same thing was about to happen with the particle zoo. In 1964, two physicists independently proposed a solution. Murray Gell-Mann at the California Institute of Technology and George Zweig at CERN both suggested that all these particles, the protons, neutrons, pions, kaons, and everything else in the particle zoo, were not fundamental. They were made of even smaller particles. Gell-Mann called these smaller particles quarks. The name came from a line in James Joyce's novel Finnegan's Wake. 3 quarks for muster mark. It was a whimsical choice for what turned out to be one of the most important discoveries in the history of physics. The idea was elegant. Instead of hundreds of fundamental particles, you only needed a few types of quarks combining in different ways. Just as 3 ingredients, protons, neutrons, and electrons, could explain the entire periodic table, a handful of quark types could explain the entire particle zoo. The math worked beautifully. Quarks come in 6 types, which physicists call flavors. These flavors are named up, down, charm, strange, top, and bottom. The names don't mean anything physical. They're just labels, chosen somewhat whimsically, which is a tradition in particle physics. The up and down quarks are by far the lightest and most stable. They are the ones that make up all the ordinary matter you see around you. The charm and strange quarks are heavier. The top and bottom quarks are heavier still. The top quark, discovered in 1995 at Fermilab near Chicago, is the heaviest of all. It is so heavy that a single top quark has roughly the same mass as an entire atom of gold. But despite this enormous range in mass, all 6 flavors obey the same rules when it comes to the strong force. They all carry color charge. They are all confined. The up quark has an electric charge of plus 2/3. The down quark has an electric charge of minus 1/3. A proton is made of 2 up quarks and 1 down quark. If you add up the charges, you get 2/3 plus 2/3 minus 1/3, which equals plus 1. That's exactly the charge of a proton. A neutron is made of 1 up quark and 2 down quarks. 2/3 minus 1/3 minus 1/3 equals 0. That's exactly the charge of a neutron, which is electrically neutral. The model explained everything. Every particle in the zoo could be understood as a specific combination of quarks. Particles made of 3 quarks, like protons and neutrons, are called baryons. Particles made of one quark and one antiquark are called mesons. Every single particle in that chaotic zoo fit neatly into this framework. The hundreds of seemingly random particles suddenly made sense. They were all just different arrangements of the same small set of building blocks. But here is where things get strange. Really strange. In every other case in the history of physics, when we discovered that something was made of smaller parts, we could eventually isolate those parts. We discovered that molecules are made of atoms, and we learned to isolate individual atoms. We discovered that atoms are made of protons, neutrons, and electrons, and we learned to isolate each one. The pattern was always the same. Find the building blocks, then take the thing apart and study the pieces separately. But with quarks, this pattern breaks completely. Nobody has ever isolated a single quark. Not once. Not ever. In over 60 years of trying with the most powerful particle accelerators ever built, machines that can concentrate more energy into a smaller space than anything else humans have ever created, no one has ever pulled a quark out of a proton and held it up on its own. It cannot be done. This is not a technological limitation. It is not that our accelerators aren't powerful enough. It is not that we haven't been clever enough in our experimental designs. It is a fundamental law of nature. Quarks cannot exist alone. They are permanently, irrevocably confined inside particles like protons and neutrons. And the reason for this confinement is one of the most bizarre and counterintuitive facts in all of physics. It has to do with the force that holds quarks together. A force that behaves in a way that violates every intuition you have about how forces work. Let's talk about forces for a moment, because you need to understand how every other force in nature works before you can appreciate just how strange the strong force really is. Think about gravity. Gravity is the force that keeps your feet on the ground, that keeps the moon orbiting the Earth, that keeps the Earth orbiting the sun. Gravity is an attractive force. It pulls things together. And one of its most important properties is that it gets weaker with distance. The farther apart two objects are, the weaker the gravitational pull between them. This follows what physicists call an inverse square law. If you double the distance between two objects, the gravitational force drops to 1/4 of what it was. Triple the distance and it drops to 1/9. Move 10 times farther apart and the force is only 1/100th as strong. This makes intuitive sense. The farther you are from something, the less it should pull on you. Standing on the surface of the Earth, you feel the full force of Earth's gravity. But if you fly in an airplane at 35,000 feet, you're slightly farther from the center of the Earth, and gravity is very slightly weaker. The key point is clear. Gravity weakens with distance. The farther apart things are, the weaker the attraction. Now, think about electromagnetism. This is the force responsible for electricity, magnetism, light, and all the chemical bonds that hold molecules together. It is the force that governs virtually everything you experience in daily life. From the light hitting your eyes right now to the structural integrity of the chair beneath you. Electromagnetism also follows an inverse square law. The electric force between two charged particles gets weaker as they move apart. Double the distance, 1/4 the force. This is why magnets get weaker with distance. Hold two magnets close together and you can feel a strong pull or push. Move them a few inches apart and the effect diminishes noticeably. Move them across the room and you feel nothing at all. This behavior is so deeply wired into our experience that we take it for granted. Everything we interact with in everyday life, every force we've ever experienced, gets weaker with distance. It seems like an obvious universal rule. Pull things apart and the force fades. But the strong force, the force that operates between quarks inside protons and neutrons, does something entirely different. And this is where your intuition is going to fail you completely. The strong force does get weaker at very short distances. When quarks are extremely close together, packed tightly inside a proton, the force between them is actually relatively weak. The quarks can move around almost freely within their tiny domain, bouncing off each other gently, behaving almost as if they're not attached to anything. This property is called asymptotic freedom, and it was so surprising and important when it was discovered in 1973 that it earned a Nobel Prize. But here's the shock. As you try to pull quarks apart, the strong force does not get weaker. It gets stronger. The farther apart you pull two quarks, the more intensely the force resists you. It's as if you were stretching a rubber band. The more you stretch it, the harder it pulls back. Except this is far more extreme than any rubber band. With a real rubber band, at some point the rubber reaches its limit and snaps. It breaks. The force is released. But the strong force between quarks doesn't work like that. There is no breaking point in the usual sense. The force just keeps increasing. The more energy you put into pulling the quarks apart, the more energy gets stored in the field between them. The force doesn't weaken. It doesn't plateau. It just grows. Think about what this means. With gravity, if you want to escape from a planet, you just need to reach a certain speed, the escape velocity, and then you can fly away. The planet's gravity keeps pulling, but it gets weaker and weaker as you move farther away, and eventually you're effectively free. Earth's escape velocity is about 11 kilometers per second. Reach that speed heading upward and you're gone. The planet cannot hold you. With the strong force, there is no escape velocity. No matter how fast you accelerate a quark, no matter how much energy you pour into pulling it away from its partners, the force pulling it back just keeps growing. There is no distance at which the force becomes negligible. There is no speed at which you can outrun it. You could theoretically pump the energy of an entire star into trying to rip a quark free, and it still wouldn't work. The universe simply will not allow a quark to be alone. This is not a matter of degree. It is not that the strong force is just really, really strong and we haven't built a machine powerful enough to overcome it yet. It is that the mechanism of the force itself makes isolation mathematically and physically impossible. The more energy you supply, the more the system fights back. It is a trap with no exit. Now, to understand why the strong force behaves this way, you need to understand the property that the strong force acts on. Just as electromagnetism acts on electric charge, and gravity acts on mass, the strong force acts on something called color charge. This has absolutely nothing to do with actual colors. Quarks aren't red or blue or green in any visual sense. The word color is just a label that physicists chose because they needed a way to describe a property that comes in three varieties, and colors happen to be a convenient analogy. In electromagnetism, there are two types of electric charge, positive and negative. A positive charge attracts a negative charge. Two positive charges repel each other. Two negative charges repel each other. It's a simple system with just two options. The strong force is more complex. Instead of two types of charge, there are three types. Physicists label them red, green, and blue. borrowing from the three primary colors of light. Every quark carries one of these three color charges. A quark is either red, green, or blue at any given moment. And just as electric charges must balance out in stable atoms, color charges must balance out in stable particles. A proton contains three quarks, and those three quarks always carry one red, one green, and one blue color charge. When you combine red, green, and blue light, you get white light. The colors cancel out. In physics terms, the three color charges add up to what's called color neutral, or sometimes colorless. This is the rule. Every particle that can exist freely in nature must be color neutral. This isn't just a preference or a tendency. It is an absolute law. The universe enforces it without exception. No particle with a net color charge has ever been observed in isolation. Not in cosmic rays, not in particle accelerators, not anywhere. This means a single quark, which always carries a color charge, can never exist on its own. It would be a colored object, and colored objects are forbidden from existing in isolation. A quark must always be combined with other quarks in a way that makes the total color charge cancel out. There are exactly two ways to achieve this. The first way is to combine three quarks, one red, one green, and one blue. This is what happens inside protons and neutrons. Three quarks, three colors, adding up to colorless. These three quark particles are called baryons. The second way is to combine a quark with an antiquark. Antiquarks carry anticolors. A red quark combined with an anti-red antiquark produces a colorless pair. These quark-antiquark pairs are called mesons. Those are your only options for building stable particles out of quarks. Three quarks making a baryon, or one quark and one antiquark making a meson. In both cases, the result is color neutral. In both cases, the color charge is hidden from the outside world. No individual color charge is ever exposed, and this is why a lone quark is impossible. A single quark would carry a naked color charge. It would be red or green or blue with nothing to cancel it out. The universe does not allow this. It enforces color neutrality with a mechanism so powerful that no experiment has ever broken it. But you might be wondering something. If the rule is just that color charges have to cancel out, couldn't you imagine some scenario where a quark gets ripped out of a proton and then quickly finds another quark to pair up with? Couldn't there be some brief moment, even just a fraction of a second, where a quark exists alone before combining with something else? The answer is no. And the reason goes back to how the strong force behaves with distance. Because the strong force gets stronger as quarks are pulled apart, the energy required to separate them grows without limit. You cannot gradually ease a quark out of a proton. The force resisting you keeps increasing. And long before you manage to create enough separation to isolate a quark, something else happens. Something dramatic. The energy you've been pumping into the system, the energy stored in the force field between the quarks, reaches a threshold. And at that threshold, the universe does something extraordinary. It converts that energy into matter. New quarks and antiquarks materialize out of the energy stored in the strong force field. These new quarks immediately combine with the existing quarks to form new color-neutral particles. You started by trying to pull a quark out of a proton, but instead of getting a free quark, you get new particles, more protons, more mesons, more baryons, never a bare quark. The universe reconfigures itself to prevent the exposure of a color charge. It literally creates new matter rather than allowing a single quark to exist alone. This is color confinement. It is one of the most important and most strange phenomena in all of physics. It means that quarks are real. They exist. They have measurable properties. They have mass and charge and spin. We can detect them inside protons. We can measure their interactions. We can predict their behavior with extraordinary precision. But we can never, ever hold one in isolation. They are permanently imprisoned inside the particles they form. And the bars of that prison are made of the strong force itself. A force that gets stronger the harder you try to break free. To appreciate just how different this is from anything else in nature, think about it this way. Imagine you had a magnet with a north pole and a south pole. If you cut the magnet in half, you don't get a separate north pole and a separate south pole. You get two smaller magnets, each with its own north pole and south pole. You can keep cutting and cutting, but you will never isolate a single magnetic pole. You always get pairs. Quarks are similar in some ways, but the mechanism is different and far more dramatic. With magnets, cutting in half just rearranges the existing material. With quarks, trying to separate them creates entirely new material from pure energy. The energy you put into the separation becomes the mass of new particles. This is Einstein's famous equation, E equals mc squared, in action. Energy converts to mass. The energy stored in the strong force field between separating quarks transforms into the mass of brand new quarks and antiquarks, and those new quarks immediately pair up to form color-neutral particles. The system resets. The prison reforms around every quark. Let me give you a sense of the scale here because the numbers matter. A proton is incredibly small. Its diameter is about 1 femtometer, which is 1 quadrillionth of a meter. That's a decimal point followed by 14 zeros and then a 1. You could line up roughly 50 billion protons across the width of a single human hair. To put it another way, a proton is to a grain of sand roughly what a grain of sand is to the distance from the Earth to the Moon. That is how small we are talking about. Inside that almost impossibly tiny space, 3 quarks exist, whipping around at significant fractions of the speed of light, constantly exchanging the carriers of the strong force. The quarks inside a proton are confined to a region so small that it makes an atom look like a football field by comparison. Remember, an atom is mostly empty space. The nucleus is a tiny dot at the center, but the proton itself, far from being a calm, static little ball, is a buzzing, dynamic, incredibly energetic environment, packed with activity at a scale almost too small to imagine. If you could somehow freeze time and look inside a proton, you would see a seething storm of quarks and gluons and quark-antiquark pairs flickering in and out of existence. The inside of a proton is one of the most violent and energetic environments in the known universe, all contained within a space a trillion times smaller than a grain of sand. And here is something remarkable. The quarks inside a proton are constantly changing their color charges. A quark that is red at one instant might be blue a fraction of a second later, and green a fraction of a second after that. The color charges are being exchanged continuously through interactions with the force carriers. The 3 quarks inside a proton don't have fixed colors. They are constantly cycling through all 3, trading colors back and forth. But at every single moment, the total adds up to colorless. Red plus green plus blue equals white. Always. Without exception. The system maintains this color neutrality dynamically. It's not a static arrangement. It's a furiously active process, with quarks swapping colors billions upon billions of times per second, maintaining the color balance that the universe demands. This dynamic color swapping is governed by the strong force, and the particles that carry the strong force are called gluons. Gluons are to the strong force what photons are to electromagnetism. Photons carry the electromagnetic force between charged particles. Gluons carry the strong force between color-charged particles. But gluons have a property that makes them fundamentally different from photons, a property that is ultimately responsible for confinement itself. And that property is what we're going to explore next, because it's in the behavior of gluons that we find the real answer to why quarks can never escape. The strong force doesn't just happen to be strong, its very carriers, the gluons, behave in a way that no other force carrier in the universe does. And it is this behavior that makes confinement not just likely, but inevitable. So now you understand the behavior. The strong force grows stronger with distance. It confines quarks permanently. The energy required to separate them grows without bound, creating new quarks, rather than allowing a single one to escape. But we haven't yet explained why the strong force behaves this way. We've described the behavior, but we haven't gotten to the cause. The inverse square law for gravity and electromagnetism arises from the way those fields spread out through three-dimensional space. There's a geometric reason for it. So there must be a reason the strong force grows with distance instead of weakening. And that reason lies in the nature of gluons themselves. What makes gluons so special? What property do they have that photons lack? And how does this single difference lead to the complete confinement of quarks? To answer those questions, we need to go deeper into the machinery of the strong force. We need to understand what gluons are, how they behave, and why their behavior creates a prison from which no quark can ever escape. So let's talk about gluons, because everything we've discussed so far, the strange behavior of the strong force, the fact that it grows stronger with distance instead of weaker, the permanent confinement of quarks, all of it comes down to one extraordinary property of gluons that no other force carrier in the universe possesses. And once you understand this property, the entire picture snaps into focus. To understand what makes gluons so special, we first need to understand how forces work at the most fundamental level. In modern physics, forces between particles are not transmitted through some mysterious invisible influence reaching across space. They are carried by particles. Actual physical particles that travel between the objects experiencing the force. These are called force carriers, or more formally, gauge bosons. Every fundamental force has its own carrier particle. Electromagnetism is carried by photons. These are the same photons that make up light, radio waves, X-rays, and every other form of electromagnetic radiation. When two electrons repel each other, what's actually happening at the quantum level is that they're exchanging photons back and forth. One electron emits a photon, the other absorbs it, and the result is a repulsive push between them. When a proton and an electron attract each other inside a hydrogen atom, they're also exchanging photons, but in this case, the exchange produces an attractive pull. The photon is the messenger. It carries information about the electromagnetic force from one charged particle to another. This might sound strange, the idea that forces are carried by particles flying back and forth, but it's one of the most well-tested ideas in all of physics. Quantum electrodynamics, the theory that describes how photons carry the electromagnetic force, matches experimental measurements to better than 10 decimal places. Now, here is the critical fact about photons that you need to understand. Photons do not carry electric charge, This is enormously important. The photon is the carrier of the electromagnetic force, and the electromagnetic force acts on electric charge. But the photon itself has no electric charge. It is electrically neutral, zero charge. This means that photons do not interact with each other through electromagnetism. Two photons can pass right through each other without affecting each other at all. When two flashlight beams cross in midair, they don't bounce off each other. They simply pass through the same point in space and keep going, completely unaffected. This is because photons don't carry the charge that they respond to. They are neutral messengers. They carry the force, but they don't feel it themselves. This property has profound consequences for how the electromagnetic force behaves. Because photons don't interact with each other, the electromagnetic field between two charged particles spreads out freely in all directions. It radiates outward like the surface of an expanding balloon. As it spreads, it gets thinner. The same amount of force is distributed over a larger and larger area. This is exactly why the electromagnetic force follows an inverse square law. Double the distance and the field has spread over 4 times the area, so the force at any given point is 1/4 as strong. It's simple geometry. The field spreads because nothing stops it from spreading. The photons carrying the force fly outward in all directions, and there's nothing pulling them back, nothing making them stick together, nothing preventing them from dispersing. They're neutral. They don't care about each other. They don't even know each other exists. Two photons can occupy the same point in space at the same time, without any interaction whatsoever. This indifference, this complete lack of self-interaction, is what allows the electromagnetic field to thin out with distance. And that thinning is what makes the force weaken. The geometry of three-dimensional space does the rest. A field that spreads freely in 3 dimensions weakens according to the inverse square of the distance. This is as reliable as mathematics itself. Now let's turn to gluons. Gluons are the carriers of the strong force, the force that acts between quarks. In the same way that photons carry the electromagnetic force between electrically charged particles, gluons carry the strong force between color-charged particles. When two quarks interact inside a proton, they do so by exchanging gluons. One quark emits a gluon, the other quark absorbs it, and the result is the strong force pulling them together. So far, this sounds exactly like electromagnetism. Just swap photons for gluons and electric charge for color charge. But here is where everything changes. Here is the single fact that makes the strong force fundamentally, radically, irreversibly different from every other force in nature. Gluons carry color charge. Let me say that again, because it might be the most important sentence in this entire story. Gluons, the particles that carry the strong force, themselves carry the very charge that the strong force acts on. The messenger is not neutral. The messenger is charged. Each gluon carries a combination of a color and an anticolor. For example, a gluon might carry red and anti-blue, or green and anti-red, or blue and anti-green. There are 8 distinct types of gluons, each carrying a different combination of color and anticolor charges. This is completely unlike photons. A photon carries the electromagnetic force but has no electric charge. A gluon carries the strong force and has color charge. This one difference, this single asymmetry between the two forces, changes absolutely everything about how the strong force behaves. Think about what this means. If gluons carry color charge and the strong force acts on color charge, Then gluons interact with other gluons. They don't just fly between quarks like neutral messengers delivering a package. They grab onto each other. They pull on each other. They exchange force among themselves. A gluon emitted by one quark doesn't just travel in a straight line to another quark. It can emit more gluons along the way. Those secondary gluons can emit still more gluons. And all of these gluons are interacting with each other, pulling on each other, attracting each other through the very force they carry. The force carriers feel their own force. This is like having postal workers who can't stop opening each other's mail. The delivery system itself becomes entangled. The messengers become part of the message. The medium becomes the story. In electromagnetism, if you have two charged particles, the force between them is carried by photons that spread out in all directions. The field lines fan outward, covering more and more space, getting weaker and weaker with distance. It's clean, it's simple, it's elegant. The photons don't interact with each other, so the field behaves in a predictable, geometric way that follows the inverse square law. But in the strong force, the situation is completely different. The gluons carrying the force between two quarks don't spread out in all directions. They can't. Because gluons carry color charge and interact with each other, they attract each other. They pull themselves together into a narrow bundle. Instead of fanning out like the spokes of an umbrella, the gluon field between two quarks collapses into a tight, narrow tube. This tube of concentrated gluon field connecting two quarks is called a flux tube, and the flux tube is the key to understanding everything about confinement. Picture two quarks inside a proton. Between them, there is a flux tube, a thin string of gluon field connecting them. Now imagine pulling the quarks apart. In electromagnetism, pulling two charged particles apart causes the field between them to spread out and weaken. The force drops off with distance, but with the strong force, pulling the quarks apart doesn't cause the flux tube to spread out. The gluons in the tube are attracted to each other. They hold the tube together. As you stretch the distance between the quarks, the tube doesn't thin out or disperse. It stays narrow. It stays concentrated. It just gets longer. And here's the crucial part. Because the tube maintains a roughly constant thickness regardless of how long it is, the energy stored in the tube is proportional to its length. Double the distance between the quarks and you double the length of the tube, which doubles the energy stored in it. Triple the distance and you triple the energy. The energy doesn't diminish with distance the way it does for gravity or electromagnetism. It grows linearly. This means the force required to keep pulling the quarks apart doesn't decrease. It stays roughly constant no matter how far apart they are. And in practice, because of the dynamics of the gluon field, it actually increases somewhat with distance before the tube eventually does something dramatic, which we'll get to. But the fundamental point is this: the flux tube stores more and more energy as you stretch it. The force never weakens. The prison never loosens its grip. And the reason is entirely because gluons interact with each other, holding the flux tube together and preventing the field from spreading out the way an electromagnetic field would. Let me make this more concrete with an analogy. Imagine you have two balls connected by a rubber band. If you pull the balls apart, the rubber band stretches and the force pulling them back together increases. The farther apart you pull them, the harder the rubber band pulls back. Now imagine you have two balls connected by an electric field, like two charged particles. As you pull them apart, the field spreads out, the force weakens, and eventually you barely feel any pull at all. The flux tube between quarks behaves much more like the rubber band than like the electric field. Except it's a rubber band that never breaks in the ordinary sense. You can keep stretching it and it keeps storing more energy, pulling harder and harder, never snapping, never letting go. And unlike a rubber band, which is a passive object that simply resists being stretched, the flux tube is an active, dynamic structure. It's made of gluons that are constantly interacting with each other, constantly reinforcing the tube's structure, constantly maintaining the prison walls from the inside. The flux tube is alive with energy. It buzzes with quantum activity. It is not a static string stretched between 2 points. It is a roiling, seething cylinder of pure force, held together by its own self-interaction. But this analogy, while helpful, actually undersells what's happening. Because a real rubber band is made of atoms and molecules. It has a finite strength. At some point, the molecular bonds break and the rubber snaps. The flux tube doesn't work that way. The energy in a flux tube doesn't have a maximum. You can keep pumping energy into it indefinitely. And as we'll explore in detail shortly, when enough energy is stored in the tube, something far more dramatic than breaking happens. But before we get there, I want to make sure you fully understand why the gluon self-interaction creates this flux tube structure, because this is the heart of the entire mechanism. In electromagnetism, imagine the electric field between a positive charge and a negative charge. Field lines radiate outward from the positive charge and curve around to terminate on the negative charge, but these field lines spread out in all directions. Near the charges, the field is strong because the lines are close together. Far from the charges, the field is weak because the lines have spread apart. Each field line goes its own way, independent of all the others, because photons don't interact with each other. Now imagine the gluon field between two quarks. Field lines, or more precisely the lines of color force, connect one quark to the other. But unlike electromagnetic field lines, these color field lines are not independent. The gluons that make up these field lines carry color charge and attract each other. Field lines that try to spread apart get pulled back together by the mutual attraction of the gluons. It's as if the field lines were sticky. They cling to each other. They bunch together into a tight bundle rather than spreading out. The result is a tube, a cylinder of intense gluon field connecting the two quarks, with very little field existing outside the tube. This is sometimes described by saying that the strong force has a property called anti-screening, while electromagnetism has a property called screening. In electromagnetism, the vacuum between two charges is filled with virtual particle-antiparticle pairs that pop in and out of existence. These virtual electron-positron pairs are a natural consequence of quantum mechanics. They appear for the briefest of instants, borrow energy from the vacuum, and then vanish again. While they exist, these virtual pairs partially cancel out the electric field, weakening it. The positive end of a virtual pair orients toward a negative charge, and the negative end orients toward a positive charge, creating a slight counterfield that reduces the original field's strength. This is screening. The vacuum itself acts like a dielectric medium, weakening the electromagnetic force at longer distances. In the strong force, the opposite happens. The gluon self-interaction causes the vacuum to strengthen the color field at longer distances rather than weakening it. The gluons don't screen the force, they anti-screen it, they amplify it. The more space there is between two quarks, the more the gluon field builds up and concentrates, making the force stronger. This is the microscopic origin of the flux tube. The gluon self-interaction, the fact that gluons carry color charge and attract each other, causes the color field to squeeze into a narrow tube rather than spreading out. And the energy stored in that tube grows with its length, which is why the strong force doesn't weaken with distance. Now, I want to emphasize something important. This isn't just a theoretical idea or a mathematical abstraction. The flux tube has been observed, indirectly but convincingly, in multiple ways. One of the most powerful tools physicists have for studying the strong force is called lattice quantum chromodynamics, or lattice QCD. This is a computational technique where physicists simulate the behavior of quarks and gluons on a supercomputer. They divide space and time into a grid of points, a lattice, and calculate the gluon field at each point according to the mathematical rules of quantum chromodynamics. These calculations are extraordinarily demanding. They require tracking the interactions of countless gluon fields at millions of lattice points, evolving the system step by step and averaging over many different possible configurations. A single simulation can take months of computing time on some of the world's most powerful supercomputers, machines capable of performing quadrillions of calculations per second. But the results are remarkable and they are unambiguous. When you calculate the gluon field between two quarks using lattice QCD, you see the flux tube. It appears clearly in the simulations as a bright, concentrated cylinder of color field connecting the two quarks, with the field intensity dropping sharply outside the tube. The simulations confirm that the energy stored in the tube grows linearly with the distance between the quarks, exactly as the flux tube model predicts. This is one of the most important confirmations of our understanding of confinement. There's another way to see the flux tube in action, and that's through something called Regge trajectories. When physicists plot the squared masses of hadrons, particles made of quarks, against their angular momentum or spin, they find that the values fall on straight lines. This pattern was discovered in the 1960s, before quarks were even proposed, and it puzzled physicists for years. But once the flux tube model was developed, the pattern made perfect sense. If you have two quarks connected by a flux tube and you spin them around each other, the tube acts like a string. A longer string stores more energy, which means more mass, and a spinning string has an angular momentum related to its length. The relationship between mass and angular momentum for a spinning string is exactly a straight line, which is exactly what the Regge trajectories show. The pattern in the masses of hadrons is a direct reflection of the flux tube structure connecting their quarks. Let me describe the flux tube in a bit more physical detail so you can really picture it. The diameter of a flux tube is roughly 1 femtometer, which is about the same as the diameter of a proton. The energy density inside the tube is staggering, comparable to the energy density packed inside an atomic nucleus itself. One of the most extreme concentrations of energy found anywhere in nature. It rivals the conditions that existed in the first microseconds after the Big Bang. All of this energy is packed into a tube that's thinner than an atomic nucleus and can extend, in principle, as far as you want, as long as you keep pumping in energy. The tension in the tube, the force it exerts trying to pull the quarks back together, is about 14 tons. 14 tons of force in a tube thinner than a proton. This is sometimes expressed in particle physics units as about 1 giga-electron-volt per femtometer, meaning that for every femtometer you stretch the tube, you add about 1 giga-electron-volt of energy. To put that number in context, the mass of a proton corresponds to roughly 1 giga-electron-volt. So stretching the flux tube by just 1 femtometer adds roughly the equivalent of 1 proton's worth of mass energy to the system. Stretch it by 10 femtometers, and you've added 10 protons worth of energy. That energy has to go somewhere, and it does. It goes into creating new particles, but that's a story for later. Now let me connect all of this back to the fundamental difference between gluons and photons, because I want you to see how one simple property, whether the force carrier is charged or neutral, leads to two completely different behaviors of force with distance. With photons, the force carrier is neutral. Photons don't interact with each other. The electromagnetic field spreads out freely. The force weakens with distance following an inverse square law. Charged particles can be separated and isolated. You can have a lone electron or a lone proton. Electromagnetic charges can exist independently. With gluons, the force carrier is charged. Gluons interact with each other through the very force they carry. The color field doesn't spread out. It collapses into a flux tube. The energy in the tube grows with distance. The force doesn't weaken. Color-charged particles cannot be separated. You can never have a lone quark. Color charges are permanently confined. Same basic framework. Force carried by particles, but one difference in the properties of the carrier particle leads to two completely opposite outcomes. It's remarkable how much hinges on this one detail. If gluons were electrically neutral in the color sense, if they didn't carry color charge, the strong force would behave much like electromagnetism. It would weaken with distance. Quarks could be pulled apart and isolated. Confinement wouldn't exist. Protons would be fragile objects that could be torn apart with enough energy, revealing their constituent quarks. The entire structure of matter as we know it would be different. But gluons do carry color charge, and that single fact creates confinement, creates the flux tube, creates the bizarre behavior where more force means more resistance, and ultimately creates the universe we live in, where quarks are permanently hidden inside the particles they form. There's something else about gluons that deserves attention because it adds another layer of complexity to this already remarkable picture. I mentioned that there are 8 types of gluons. You might wonder why 8. If each gluon carries one color and one anticolor, and there are 3 colors and 3 anticolors, you might expect 9 combinations. Red anti-red, red anti-blue, red anti-green, blue anti-red, blue anti-blue, blue anti-green, green anti-red, green anti-blue, and green anti-green. That's 9. But one of these combinations, the one that is an equal mixture of red anti-red, blue anti-blue, and green anti-green, turns out to be color neutral. It would be a colorless gluon. And a colorless gluon wouldn't interact with color-charged particles. It would be invisible to the strong force. It would behave like a photon, able to travel freely without confinement. No such particle has ever been observed, and theoretical analysis shows it doesn't exist as an independent gluon state. So we're left with 8 gluons, all carrying some net color charge, all interacting with quarks and with each other. This means that gluons themselves are confined, just like quarks. You can never observe a lone gluon in isolation. A free gluon would carry a color charge and would be visible to the color force, subject to the same confinement rules as quarks. Gluons are trapped inside hadrons alongside the quarks they bind. The jailer is in the same prison as the inmates. This is another way the strong force differs radically from electromagnetism. Photons roam freely across the universe. They travel billions of light years from distant galaxies to your eye. You interact with photons every moment of every day. But gluons never travel freely. They never escape the confines of the hadrons they hold together. They live and die inside the femtometer scale prison of the proton, never once venturing into the outside world. The fact that gluons carry color charge also means that gluons can interact with other gluons without any quarks being involved at all. Physicists predict that there should exist particles called glue balls, which are made entirely of gluons bound together by their mutual color interactions, with no quarks present whatsoever. Think about how bizarre that is. The force carriers themselves, bound together by the very force they're supposed to carry, forming a particle made of pure force. It is as if you could ball up a handful of gravity and hold it in your hand. Finding experimental evidence for glue balls has been challenging because they tend to mix with ordinary quark-based particles that have similar properties, making it hard to identify a pure glue ball state. Several candidate particles have been identified, but none has been confirmed beyond doubt. Still, the theoretical prediction is clear. The self-interaction of gluons is so strong that gluons can bind to each other and form composite objects. The force carriers themselves become the building blocks of new particles. Nothing like this happens in electromagnetism. Photons don't bind to each other to form photon balls. They can't, because they don't interact with each other. But gluons can and do form bound states, at least in theory, because they carry the charge they respond to. Let me step back and put all of this in perspective. We've been diving deep into the details of gluon behavior, flux tubes, and color charge, but I want to make sure the big picture is clear. Everything we've discussed comes down to one central idea. The reason quarks can never escape a proton is that the force holding them together doesn't weaken with distance. And the reason the force doesn't weaken is that the particles carrying the force, the gluons, interact with each other. This self-interaction squeezes the force field into a narrow tube that stores more energy the longer it gets. Pulling quarks apart doesn't weaken their bond, it strengthens it. Every bit of energy you invest in trying to separate them gets absorbed by the flux tube, making the tube longer and storing more energy. The system fights you at every step, and it keeps fighting, harder and harder, no matter how much energy you bring. So what happens if you bring a truly enormous amount of energy? What happens if you slam two protons together at nearly the speed of light in a machine like the Large Hadron Collider, the most powerful particle accelerator ever built? A machine that can concentrate more energy into a single collision than exists in the center of a star? What happens when the flux tube is stretched to its breaking point? Does it finally snap? And if it does, do the quarks finally escape? The answer is no. The quarks still don't escape. But what does happen is spectacular. The flux tube does reach a point where something dramatic occurs. But instead of releasing a free quark, the universe pulls off a trick so elegant, so perfectly designed to preserve confinement, that it almost seems like the laws of physics were written specifically to prevent quarks from ever being alone. The energy in the stretched tube doesn't release a quark, it creates new quarks, and those new quarks immediately form new confined particles. The prison doesn't break, it multiplies. And understanding how this happens, understanding the mechanics of what physicists call string breaking and hadronization, is what we need to explore next. So now we arrive at the moment of truth. You understand that quarks are bound together by the strong force. You understand that this force is carried by gluons, and that gluons carry color charge, which means they interact with each other. You understand that this self-interaction squeezes the gluon field into a narrow flux tube connecting quarks, and that this tube stores more energy the longer it gets. The force doesn't weaken with distance. It stays constant or even grows. The prison tightens its grip the harder you pull. But what actually happens when you pull hard enough? What happens when you take two quarks inside a proton and pour enormous amounts of energy into trying to separate them? Does the flux tube just stretch forever, getting longer and longer and storing more and more energy without limit? Or does something eventually give? Something does give, but it's not what you'd expect. The flux tube doesn't simply snap like a rubber band, releasing the quarks to fly apart. What happens instead is far more extraordinary, and it is, without exaggeration, one of the most elegant mechanisms in all of physics. Let's walk through it step by step. Imagine a proton sitting quietly in space. Inside it, three quarks are buzzing around in their tiny femtometer scale domain, connected by flux tubes of gluon field, held together by the strong force. Everything is in balance. The quarks have enough energy to move around within the proton, but not enough to escape. The flux tubes are short and the energy stored in them is modest. Now imagine you slam another proton into this one at nearly the speed of light. This is exactly what happens at the Large Hadron Collider at CERN, the most powerful particle accelerator on Earth. The LHC accelerates protons to 99.999991% of the speed of light. At this speed, each proton carries about 6,500 times more energy than its rest mass. When two protons collide head-on at these energies, the quarks inside them can receive enormous kicks. A quark that was happily bouncing around inside its proton suddenly gets slammed with so much energy that it starts flying away from its partners at tremendous speed. The flux tube connecting it to the other quarks begins to stretch. As the quark flies outward, the flux tube grows longer. And as we discussed, the energy stored in the tube increases with its length, steadily and relentlessly. One femtometer of tube stores about 1 giga-electron-volt of energy, roughly the mass energy of a proton. 2 femtometers stores 2 giga-electron-volts. 3 femtometers stores 3 giga-electron-volts. The fleeing quark is dragging behind it a lengthening tail of concentrated gluon field, and that tail is getting heavier and heavier with stored energy. The quark is trying to escape, but the tube is pulling it back with a force of about 14 tons. Now here is where Einstein enters the picture. Einstein's most famous equation, E equals mc squared, tells us that energy and mass are interchangeable. They are two forms of the same thing. Energy can be converted into mass, and mass can be converted into energy. This isn't just a theoretical statement. It's been confirmed in countless experiments. Every nuclear reactor, every nuclear weapon, every particle accelerator collision demonstrates this equivalence. Mass can become energy, and energy can become mass. As the flux tube stretches and stores more and more energy, it eventually reaches a critical threshold. The energy stored in the tube becomes large enough to equal the mass of a quark-antiquark pair. Remember, quarks have mass. An up quark has a mass of about 2.2 mega-electron-volts, which stands for mega-electron-volts. A down quark has a mass of about 4.7 mega-electron-volts. These are small masses by particle physics standards. The energy stored in even a short flux tube vastly exceeds the mass of a quark-antiquark pair. And when the energy in the tube is sufficient, something remarkable happens. The tube breaks, but not the way a rubber band breaks. When a rubber band snaps, the two pieces fly apart with nothing connecting them anymore. The tension vanishes, the force disappears. When a flux tube breaks, something completely different occurs. At the point where the tube breaks, a new quark-antiquark pair materializes out of the energy stored in the tube. The energy of the gluon field is converted directly into the mass and kinetic energy of a brand new quark and a brand new antiquark. These particles didn't exist a moment ago. They were created from pure energy, pulled into existence by the intense color field of the stretched flux tube. And here is the critical part. The new quark immediately attaches to one end of the broken tube. The new antiquark attaches to the other end. So instead of having one broken tube with free color charges at each end, you now have two shorter tubes, each with quarks at both ends. Each of these new shorter tubes is a complete color-neutral particle, where before you had one proton with a quark being ripped away, you now have two separate hadrons, two confined systems, two prisons, each holding its inmates securely. Let me be very specific about what happens. Say you start with a proton, which contains two up quarks and one down quark. You slam it with enough energy that one of the up quarks goes flying. The flux tube between that departing up quark and the remaining quarks stretches. Energy builds in the tube. The tube breaks, and a new quark-antiquark pair appears at the break point. Let's say a down quark and an anti-down quark materialize. The anti-down quark pairs up with the fleeing up quark. An up quark plus an anti-down quark makes a particle called a pi plus meson, or a positive pion. Meanwhile, the new down quark joins the two quarks that stayed behind, reconstituting something that looks like a neutron or another baryon. You started with one proton and tried to pull a quark out. You ended up with a baryon and a meson. Two particles instead of one, but zero free quarks. And if the fleeing quark has enough energy, the process doesn't stop there. The pion that just formed is itself moving fast, dragged along by the momentum of the original escaping quark. The flux tube between the quark and antiquark inside the pion can also stretch if there's enough energy. That tube can also break, creating another quark-antiquark pair, which forms more mesons. Those mesons can also break apart if there is still enough energy. The process cascades. One quark trying to escape can produce a shower of new particles. 10, 20, 50, even hundreds of hadrons, all created from the energy that was pumped into the original collision. But no matter how many particles are created, no matter how energetic the cascade becomes, every single particle that emerges is color neutral. Every single one is a confined system of quarks and antiquarks. Not a single bare quark or bare gluon ever appears. The universe enforces confinement at every step, at every break, at every moment. It is relentless. It never fails. This cascade process has a name. Physicists call it hadronization, or sometimes fragmentation. It is the process by which the energy of the fast-moving quark or gluon is converted into a spray of hadrons. And it happens every single time a quark is knocked hard enough to start escaping a proton. There are no exceptions. In over 50 years of colliding particles at ever higher energies, in millions upon millions of collisions studied at accelerators around the world, hadronization has never once failed to produce confined particles. Not a single free quark has ever been observed coming out of a collision. Not one. The showers of particles produced by hadronization are called jets. A jet is a narrow cone of hadrons, mostly pions and kaons and other light mesons, all moving in roughly the same direction. The direction of the jet corresponds to the direction the original quark was moving when it was knocked out of the proton. By studying the properties of jets, their energy, their width, the number and types of particles they contain, physicists can learn about the quark that started the cascade. In a sense, jets are the closest we can get to observing a quark. We can't see the quark itself, but we can see the spray of particles it creates as confinement reasserts itself. And from that spray, we can deduce the quark's properties. Jets were first observed in 1975 at the Stanford Linear Accelerator Center, known as SLAC, in California. Physicists were colliding electrons with positrons at high energies. When an electron and a positron annihilate each other, they produce a burst of pure energy. That energy can then create a quark-antiquark pair. The quark flies off in one direction, the antiquark in the opposite direction. Each one tries to escape, each one stretches a flux tube behind it, each flux tube breaks and produces a cascade of hadrons. The result is two jets of particles flying in opposite directions. When physicists first saw these two jet events in their detectors, it was powerful evidence that quarks were real objects, not just mathematical constructs. The jets showed that something point-like, something with the quantum numbers of a quark, was being produced in the collision and then fragmenting into hadrons. You could trace the jets back to their origin and see that they came from two objects flying apart, exactly as you'd expect from a quark-antiquark pair. A few years later, in 1979, at the Petra Accelerator in Hamburg, Germany, physicists observed something even more remarkable. They saw events with three jets instead of two. Two of the jets came from the quark and the antiquark, just as before. But the third jet came from a gluon. In some collisions, the quark or antiquark radiated a high-energy gluon before hadronization occurred. That gluon, carrying color charge, also stretched flux tubes behind it as it flew outward. It also produced a cascade of new quark-antiquark pairs. It also created its own jet of hadrons, a third spray of particles emerging alongside the two quark jets. Three jet events were the first direct experimental evidence for the existence of gluons. Physicists couldn't see the gluon itself, just as they couldn't see the quarks, but they could see the jet it produced. And the properties of that third jet matched perfectly with the theoretical predictions for gluon radiation. The gluon was real, it carried color charge, and it was confined, just like quarks, producing a jet of hadrons rather than flying free. Today, at the Large Hadron Collider, jets are observed in virtually every collision. The LHC collides protons at energies of 13 trillion electron volts. At these energies, the collisions produce enormous numbers of particles. A typical collision at the LHC might produce dozens of jets, each containing many hadrons. The detectors at the LHC, massive instruments weighing thousands of tons and containing millions of sensors, are designed specifically to measure these jets. They record the energy and direction of every particle in each jet, allowing physicists to reconstruct what happened in the collision with extraordinary precision. And every single one of those jets confirms confinement. Every collision, every jet, every particle tells the same story. Quarks and gluons are produced in the collision. They try to fly apart. Flux tubes stretch, The tubes break. New quark-antiquark pairs are created. Hadrons form, and nothing with a bare color charge ever escapes. The process is so reliable, so completely without exception, that physicists don't even think about it as something that needs to be checked anymore. Confinement is simply how the universe works. It is as dependable as the sunrise. Let me give you a vivid picture of what a collision at the LHC actually looks like. Two protons approach each other at nearly the speed of light. Each proton is a tiny ball about 1 femtometer across, containing 3 quarks swimming in a sea of gluons and virtual quark-antiquark pairs. The 2 protons travel in opposite directions around the 27-kilometer ring, guided by powerful superconducting magnets cooled to a temperature colder than outer space. At the collision point, the 2 protons smash into each other. At these energies, what actually collides is not the proton as a whole, but a single quark or gluon from one proton hitting a single quark or gluon from the other. This is called a hard scattering event. The colliding quark or gluon is kicked violently, sent flying at high speed in a new direction with enormous energy. It feels the recoil of the impact like a billiard ball struck by a cue, except the energies involved are trillions of times greater than anything in ordinary experience. The other quarks in each proton, the ones that didn't participate in the hard collision, continue moving roughly in their original directions. They're called spectator quarks, and they produce their own softer jets along the beamline. The hard scattered quarks and gluons fly outward from the collision point. Within a distance of about 1 femtometer, the flux tubes connecting them to their former partners begin to stretch. Within a few femtometers, the first pair creation events occur. New quarks and antiquarks pop into existence. Within about 10 femtometers, a full cascade is underway. The original quark or gluon has spawned dozens of new quarks and antiquarks, all pairing up into hadrons. This entire process, from the initial collision to the formation of hadrons, takes about 100 millionth of a trillionth of a second. It is almost instantaneous. The hadrons then fly outward into the detector, where they are measured. Some of these hadrons are stable, like protons and neutrons. Others are unstable, like pions and kaons, and they decay into other particles within nanoseconds or less. The detector records everything, building up a picture of what emerged from the collision. From this picture, physicists can work backward, using the laws of quantum chromodynamics to figure out what happened at the fundamental level. They can determine what quarks and gluons were involved, how much energy they had, what angles they scattered at, and what forces acted between them. This entire process, from collision to jet formation to detection, is one of the most precise tools in all of science. The theory predicts the rates of different types of events, the shapes and sizes of jets, the ratios of different particles produced, and the predictions match the data with the precision of a few percent or better across thousands of different measurements. Quantum chromodynamics is one of the most precisely confirmed theories in the history of physics. But here is what I really want you to understand. Every single one of these confirmations, every measurement, every data point is an indirect observation. We never see a quark, we never see a gluon, we never see a flux tube. We see only the hadrons that emerge after confinement has done its work. Everything we know about quarks and gluons, we know from studying the particles they produce when they're confined. It's like studying a prisoner by looking at the letters they send out. You never see the prisoner directly, but from those messages you can learn an extraordinary amount about who they are and what they're doing inside. Now, I want to address something that might be bothering you. This whole picture of flux tubes stretching and breaking, of quark-antiquark pairs popping out of the vacuum, it might sound abstract. It might sound like a physicist's fairy tale, a nice story that explains the data but isn't really what's happening. So let me be clear about this. This is really what happens. Pair creation from the vacuum is not a metaphor. It's not an approximation. It's not a simplification for popular audiences. It is a real, physical process that occurs constantly in quantum field theory. The vacuum, the empty space between and around particles, is not truly empty. In quantum mechanics, the vacuum is a seething, roiling ocean of activity. Virtual particles, particle-antiparticle pairs, are constantly appearing and disappearing everywhere in space. They borrow energy from the vacuum for an incredibly brief moment, flicker into existence, and then vanish again before the universe can notice the energy debt. This sounds crazy, but it's been confirmed experimentally. The Casimir effect, predicted in 1948 and confirmed experimentally decades later, is a measurable force between two metal plates placed very close together in a vacuum. The force exists because the virtual particles in the vacuum between the plates are slightly different from those outside the plates. The fact that this force can be measured and matches predictions means that virtual particles are real and have physical consequences. In the context of the strong force, what happens when a flux tube stretches is that the intense color field inside the tube provides the energy needed to promote virtual quark-antiquark pairs into real, permanent particles. The pairs don't need to borrow energy from the vacuum anymore. The energy is right there, stored in the flux tube, available and abundant. The field converts virtual pairs into actual pairs, transforming fleeting quantum ghosts into solid, enduring particles with real mass and real momentum. This is sometimes called the Schwinger mechanism, named after physicist Julian Schwinger, who first described the theoretical framework for pair creation in strong fields. Schwinger showed that when an electric field is strong enough, it can spontaneously create electron-positron pairs from the vacuum. The same basic physics applies to the color field in a flux tube, except the color field inside a flux tube is enormously stronger than any electric field we can create in a laboratory. The conditions for pair creation are met almost immediately once the tube starts stretching. This is why there is no gradual process of a quark slowly separating from a proton. There is no moment where a quark is halfway out. The pair creation happens so quickly and so inevitably that confinement is maintained at every instant. As soon as you start pulling a quark away, as soon as the flux tube begins to stretch, the conditions for pair creation are being approached. By the time the tube has stretched a few femtometers, the first pairs are already appearing. The process is explosive and near instantaneous. The quark never gets more than a few femtometers from its partners before the vacuum steps in and creates new quarks to maintain confinement. The universe acts faster than the quark can move. There's a beautiful symmetry in this process. The energy you put into trying to free a quark is the very energy that creates new quarks to prevent the first one from being free. Your effort is self-defeating. The harder you try, the more particles you create, and the more thoroughly confinement is enforced. The system is self-correcting. It always returns to a state where every quark is confined. This self-correcting nature is why confinement is not just a rule that physicists impose on the theory. It's a physical consequence of the dynamics. It emerges naturally from the equations of quantum chromodynamics. You don't have to add confinement to the theory by hand. You don't have to assume it or postulate it. It follows from the basic ingredients: quarks with color charge, gluons that carry color charge and interact with each other, and the rules of quantum field theory. Put those ingredients together and confinement comes out automatically. The theory predicts it. The experiments confirm it. The universe enforces it. Having said all this, I should be honest about something. While confinement is confirmed beyond any reasonable doubt by experiments, and while lattice QCD calculations show it clearly, physicists have not yet proven confinement rigorously from the fundamental equations of quantum chromodynamics. This is actually one of the most important unsolved problems in theoretical physics. The Clay Mathematics Institute has offered a $1 million prize for a rigorous mathematical proof that quantum chromodynamics has a mass gap, which is closely related to proving confinement. The mass gap means that the lightest particle in the theory has a non-zero mass, which is connected to the idea that color-charged objects can't propagate freely across large distances. Physicists are confident that QCD does confine quarks because the evidence is overwhelming. But writing down a complete mathematical proof has turned out to be extraordinarily difficult. The equations of QCD are so complex, so deeply nonlinear because of the gluon self-interaction, that solving them exactly is beyond current mathematical techniques. This is partly why lattice QCD requires such enormous computing power. The equations can't be solved with pen and paper. They have to be computed numerically, point by point, on a space-time lattice. The fact that confinement is so well established experimentally, but so hard to prove, mathematically tells you something about the depth and difficulty of the strong force. It is the most complicated of the four fundamental forces, and in many ways, the least understood at a deep mathematical level, even though we can calculate its effects with remarkable precision. Let me also mention one more thing about hadronization that reveals just how thoroughly the universe enforces confinement. When a flux tube breaks and new hadrons form, the process isn't random. The types of particles that are produced, their abundances, their energies, all follow specific statistical patterns that can be predicted using models of how the flux tube fragments. These models have names. The Lund string model, developed at Lund University in Sweden, is the most famous. In this model, the flux tube is treated mathematically as a relativistic string, a one-dimensional object with tension that stores energy proportional to its length. When the string breaks, it produces hadrons according to specific probability distributions. The Lund string model has been tested against millions of collisions at accelerators around the world, and it works extraordinarily well. It correctly predicts the ratios of different types of hadrons produced, the distributions of their momenta, the correlations between particles in a jet. This success means that the flux tube picture, the idea of a string of gluon field connecting quarks that breaks by pair creation, is not just a qualitative story. It is quantitatively accurate. It describes reality. So let me summarize what we've learned in this stretch of our journey. When you try to pull a quark out of a proton, the flux tube connecting it to the other quarks stretches. Energy builds in the tube. When enough energy has accumulated, the tube breaks by creating new quark-antiquark pairs from the energy stored in the field. These new quarks pair up with the existing ones to form new hadrons. Every particle that emerges is color neutral. No bare quark ever appears. If you put in more energy, you get more breaks, more pairs, more hadrons. The result is a jet, a spray of particles all moving in roughly the direction the original quark was traveling. Jets are observed in every high-energy collision. They confirm confinement. They confirm the existence of quarks and gluons. They confirm the flux tube picture, and they demonstrate conclusively that the universe will not allow a quark to exist alone under any circumstances. You might be wondering, given all of this, how we can be so sure that quarks are real. If we can never see them, if we can never isolate them, if every experiment produces only confined hadrons and never a bare quark, then how do we know quarks aren't just a useful mathematical fiction? Maybe the hadrons are the real fundamental objects, and quarks are just a convenient bookkeeping device that helps us organize the particle zoo. Maybe there are no actual point-like objects inside the proton. Maybe we're fooling ourselves. This is a legitimate question. It was debated hotly in the 1960s and 1970s when the quark model was first proposed. Many respected physicists were skeptical. How can something be real if you can never observe it directly? It's a deep philosophical question about what it means for a scientific entity to exist. And the answer comes from experiments that don't try to pull quarks out of protons, but instead look inside protons while leaving them intact. These experiments provide some of the most compelling evidence in all of physics that quarks are not just mathematical conveniences, but real, physical objects with definite properties. And that is exactly what we need to understand next. This question, whether quarks are real or merely useful fictions, is not just a philosophical curiosity. It gets to the heart of what science is and what it means for something to exist. And the answer physicists arrived at didn't come from pulling quarks out and examining them. It came from a completely different approach. Instead of trying to tear the proton apart and extract its pieces, physicists decided to look inside the proton while leaving it intact. They did this by firing high-energy particles at protons and watching how those particles bounced off. The technique is called deep inelastic scattering, and it is one of the most important experiments in the history of physics. The basic idea is simple and elegant. If you want to know what's inside something, you throw something small at it and see what happens. This is actually how we figured out the structure of the atom in the first place. In 1911, Rutherford and his colleagues fired alpha particles at a thin gold foil and observed how they scattered. Most alpha particles pass straight through, but a few bounce back at large angles. This told Rutherford that the atom was mostly empty space, with a tiny, dense nucleus at its center. The pattern of scattering revealed the structure. Deep inelastic scattering works on the same principle, but at a much smaller scale. Instead of firing alpha particles at atoms, physicists fired high-energy electrons at protons. The electrons were accelerated to enormous energies at the Stanford Linear Accelerator Center, SLAC, in the late 1960s. At high enough energies, the wavelength of the electron becomes small enough to probe the internal structure of the proton. This is a consequence of quantum mechanics. Every particle has an associated wavelength, called its de Broglie wavelength, and that wavelength decreases as the particle's energy increases. A low-energy electron has a wavelength much larger than a proton, so the proton appears as a featureless blob. But a high-energy electron has a wavelength much smaller than a proton, small enough to resolve structures inside it. When the SLAC physicists fired these high-energy electrons at protons, they found something remarkable. The electrons didn't bounce off the proton as if it were a smooth, uniform ball. Instead, some electrons scattered at very large angles, bouncing almost straight back the way they came. This was the same signature Rutherford had seen when he discovered the atomic nucleus. Large angle scattering means the incoming particle hit something small, hard, and point-like inside the target. If the proton were a uniform blob of matter, the electrons would scatter gently, deflecting at small angles like marbles rolling over a soft mound of clay. But that's not what happened. Some electrons ricocheted violently, changing direction by huge amounts, as if they had struck something tiny and rigid embedded inside the proton. The electrons were bouncing off tiny compact objects inside the proton. The physicists analyzed the scattering patterns in detail. They measured how many electrons scattered at each angle and with what energy. They compared these measurements with theoretical predictions for different possible structures inside the proton. If the proton were made of a continuous distribution of charge and matter, the scattering pattern would look one way. If it contained discrete point-like objects, the pattern would look very different. The data was unmistakable. The scattering patterns matched point-like objects perfectly. The electrons were hitting tiny, hard constituents, with spin 1/2 and fractional electric charges. The charges measured were +2/3 and -1/3. Exactly the charges predicted for up quarks and down quarks. The spin was exactly what quark theory predicted. The objects behaved as if they were free particles, barely interacting with each other, just sitting there inside the proton waiting to be hit. At the time, these point-like objects were cautiously called partons, a name coined by Richard Feynman, who wanted to avoid prematurely identifying them with quarks until the evidence was overwhelming. But as more data accumulated, as the measurements became more precise, as the properties of the partons were measured in greater and greater detail, it became clear that partons and quarks were the same thing. The point-like objects inside the proton had exactly the properties that the quark model predicted, right down to the precise values of their electric charges and their quantum mechanical spin. This was the breakthrough. The deep inelastic scattering experiments at SLEC, conducted between 1967 and 1973, provided the first direct evidence that protons contain point-like constituents with the exact properties predicted by the quark model. The experiments were led by Jerome Friedman, Henry Kendall, and Richard Taylor, who shared the Nobel Prize in Physics in 1990 for this discovery. Their work transformed quarks from a theoretical hypothesis into an observed reality. But there was a puzzle embedded in this discovery that took several years to resolve, and the resolution turned out to be one of the most profound insights in all of physics. The puzzle was this: the deep, inelastic scattering experiments showed that the quarks inside the proton were behaving as if they were nearly free. They weren't interacting strongly with each other. They were just sitting there like billiard balls on a table, easily knocked aside by an incoming electron. But wait, we've spent this entire journey talking about how the strong force is incredibly powerful, how it confines quarks permanently, how the force grows stronger with distance. How can the quarks inside a proton be nearly free if the force holding them there is the strongest force in the universe? The answer is asymptotic freedom, and it is the mirror image of confinement. We touched on this briefly earlier, but now we need to understand it fully because it is the key to reconciling everything we've discussed. Asymptotic freedom means that the strong force becomes weaker at shorter distances, not just slightly weaker, dramatically weaker. When quarks are extremely close together, separated by distances much smaller than the diameter of a proton, the strong force between them becomes very weak. The quarks behave almost as if they're free particles, barely aware of each other's existence. This is the opposite of what happens at larger distances, where the force grows stronger and eventually confines the quarks permanently. The strong force has two faces. At short distances, it's gentle and permissive, allowing quarks to move freely. At long distances, it's ferocious and unyielding, trapping quarks forever. The transition between these two regimes happens at roughly the scale of a proton, about 1 femtometer. At distances much smaller than a femtometer, quarks are nearly free. At distances comparable to or larger than a femtometer, they are confined. Asymptotic freedom was discovered in 1973 by David Gross, Frank Wilczek, and David Politzer. They showed mathematically that in quantum chromodynamics, the theory of the strong force, the coupling constant, which measures the strength of the interaction, it decreases as the energy of the interaction increases. Higher energy corresponds to shorter distances in quantum mechanics. So higher energy means shorter distances, means weaker force. This was shocking. It went against everything physicists had learned from studying other forces. Every other known force gets stronger at shorter distances when quantum effects are accounted for. Electromagnetism, for example, gets slightly stronger at very short distances because of a quantum effect called vacuum polarization. Virtual electron-positron pairs in the vacuum screen the electric charge at large distances, making it appear weaker. At shorter distances, you get past the screening, and the charge appears stronger. The strong force does the exact opposite. It gets weaker at shorter distances. The reason, once again, comes back to gluon self-interaction. The gluons that carry the strong force also carry color charge. This means that in addition to quark-antiquark pairs appearing in the vacuum, which would screen the color charge just as electron-positron pairs screen electric charge, there are also virtual gluons appearing in the vacuum, and those virtual gluons don't screen the color charge, they anti-screen it. They make the effective color charge stronger at large distances and weaker at short distances. Because of how gluon self-coupling enters the mathematics, the anti-screening contribution from gluons decisively overwhelms the screening contribution from quarks. It is not even close. The net result is that the strong force weakens at short distances. Gross, Wilczek, and Politzer received the Nobel Prize in Physics in 2004 for this discovery, which is sometimes described as one of the most important developments in theoretical physics in the second half of the 20th century. Asymptotic freedom explains the deep inelastic scattering results perfectly. When a high-energy electron hits a quark inside a proton, the interaction happens at a very short distance, much smaller than the proton's diameter. At that distance, the strong force is weak. The quark behaves almost freely. It gets knocked by the electron and responds as if it were an isolated particle, unattached to anything. This is why the scattering patterns looked exactly like electrons hitting free, point-like objects. At the scale of the interaction, the quarks effectively were free. But then, after the quark is knocked and starts flying away from its partners, the distance between them increases. And as the distance increases, the strong force grows stronger. The flux tube forms. The confinement mechanism kicks in. The quark never escapes. It hadronizes, producing a jet of particles, just as we described. So the same quark that appeared free during the high-energy collision becomes confined a fraction of a second later as it tries to move away. Both observations are correct. Quarks are free at short distances and confined at long distances. It depends entirely on the scale you're probing. This is why physicists are so confident that quarks are real. The evidence doesn't come from one type of experiment. It comes from the convergence of multiple independent lines of evidence, all pointing to the same conclusion. Deep inelastic scattering shows point-like objects inside protons with exactly the charges and spins predicted for quarks. Jet production in accelerators shows that high-energy collisions produce sprays of particles consistent with quarks and gluons hadronizing. The ratios of different particles produced in electron-positron collisions match quark model predictions with extraordinary precision. For example, the ratio of hadron production to muon production in electron-positron collisions depends directly on the sum of the squared charges of all quark flavors that can be produced. The measured ratio matches the quark model prediction exactly. If quarks didn't exist, if protons were structureless blobs, this ratio would be completely different. The 3 jet events at Petra confirmed gluons. Lattice QCD calculations using the quark and gluon model accurately predict the masses of hadrons, in some cases to better than 1% precision. The pattern of hadron masses, spins, and quantum numbers all fit the quark model perfectly. The magnetic moments of protons and neutrons, which depend on the charges and spins of their constituent quarks, match quark model predictions. The weak decays of hadrons, which involve quarks changing flavor, proceed at exactly the rates that quark theory predicts. There's no alternative model that explains all of these observations. Quarks are as real as anything in physics. More real, arguably, than many things we take for granted in everyday life. Because the evidence for quarks is more precise and more thoroughly tested than the evidence for most ordinary objects. Now let me tell you something about quarks and confinement that might be the most astonishing fact in this entire story. It has to do with mass. Your mass. The mass of everything around you. The mass of the Earth, the sun, the stars, every physical object in the universe. You are made of atoms. Atoms are made of protons, neutrons, and electrons. The mass of an atom comes almost entirely from its protons and neutrons, which together are called nucleons. Electrons contribute less than 1/20th of 1% of an atom's mass. So your mass is essentially the mass of your protons and neutrons. A proton has a mass of about 938 mega-electron volts in energy units, or about 1.67 times 10 to the minus 27 kilograms. That's a tiny number, but there are a lot of protons and neutrons in your body. About 40 billion of them. Their combined mass gives you your weight. Now, here's the question. Where does the proton's mass come from? A proton is made of 2 up quarks and 1 down quark. So you might think the proton's mass is simply the combined mass of its 3 quarks. But it's not. It's not even close. An up quark has a mass of about 2.2 mega-electron volts. A down quark has a mass of about 4.7 mega-electron volts. Add them up. 2 up quarks at 2.2 mega-electron volts each gives 4.4 mega-electron volts. 1 down quark at 4.7 mega-electron volts gives 4.7 mega-electron volts. Total quark mass inside a proton, about 9.1 mega-electron volts. But the proton's total mass is 938 mega-electron volts. The quarks contribute only about 9 mega-electron volts out of 938. That's less than 1%. The quarks, the actual fundamental particles that make up the proton, account for less than 1% of its mass. So where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the strong force, the energy of the gluon field, the energy of the flux tubes, the kinetic energy of the quarks as they zip around inside the proton at nearly the speed of light. All of this energy, through Einstein's E equals mc squared, contributes to the proton's mass. The proton is heavy not because its quarks are heavy, but because the strong force binding those quarks together contains an enormous amount of energy. And energy has mass. Think about how strange this is. If you could somehow weigh just the quarks inside a proton, stripping away the gluon field and ignoring the kinetic energy, the quarks would weigh almost nothing. About 9 million electron volts out of 938. But the gluon field, the flux tubes, the frantic motion of the quarks bouncing off the walls of their prison, all of that energy contributes 929 mega electron volts. The gluon field alone, which has zero mass in the traditional sense because gluons are massless particles, contributes the vast majority of the proton's mass purely through the energy it carries. Massless particles creating mass, a force field weighing more than the particles it binds. This is not intuitive. It defies everyday experience, but it is exactly what quantum chromodynamics predicts, and lattice QCD calculations confirm it with remarkable precision. When physicists calculate the proton mass from first principles, using the equations of QCD on a supercomputer lattice, they get a value that matches the experimentally measured proton mass to within a few percent. The theory works. The mass really does come from the energy of confinement. Let me say this again because it is genuinely one of the most profound facts in all of science. More than 99% of the mass of a proton comes not from the quarks themselves, but from the energy of the force that confines them. The mass is in the binding, not in the building blocks. The prison weighs more than the prisoners. This means that more than 99% of your body mass comes from the energy of the strong force, not from the quarks, not from the fundamental particles, from the energy of the gluon fields that hold those particles together. When you step on a scale, what you are mostly weighing is the strong force. The actual matter, the quarks and electrons that make you up as fundamental particles, contributes almost nothing to the number on the scale. You are quite literally made of energy that has been shaped into matter by confinement. Think about what this means for the nature of reality. We think of matter as solid, tangible, substantial. We think of energy as ethereal, abstract, intangible. But at the most fundamental level, matter is energy. The solidity of the world, the weight of objects, the substance of everything you touch, almost all of it is the energy of the strong force confined within protons and neutrons. The chair you're sitting on is mostly energy. The ground beneath your feet is mostly energy. Your own body is mostly energy. Not energy in some vague spiritual sense, but energy in the precise, physical, Einstein's equation sense. The energy of gluon fields, the energy of quarks moving at nearly the speed of light, the energy of the strongest force in nature, holding everything together. And this energy exists because of confinement. If quarks weren't confined, if the strong force weakened with distance like electromagnetism does, protons would be much lighter. They might not even be stable. The universe would be a fundamentally different place. There might be no atoms as we know them, no chemistry, no biology, no stars, no planets, no life. The fact that the strong force confines quarks, the fact that gluons carry color charge and create flux tubes that store energy, is not just an interesting quirk of particle physics. It is the reason matter has mass. It is the reason you exist. Confinement isn't just trapping quarks inside protons. It is creating the mass of the visible universe. Consider what happened in the very early universe. In the first microseconds after the Big Bang, the universe was so hot and so dense that quarks and gluons existed as a free plasma. The temperature was so extreme, trillions of degrees, that the quarks had enough thermal energy to overcome confinement. They roamed freely in a state of matter called quark-gluon plasma. There were no protons. There were no neutrons. There were no hadrons of any kind. Just a soup of free quarks and gluons, interacting wildly at energies where asymptotic freedom made the strong force relatively weak. But as the universe expanded and cooled, the temperature dropped. Within about 10 microseconds after the Big Bang, the universe had cooled enough that the strong force could assert itself. Confinement kicked in. The quarks and gluons were swept up into hadrons, protons, and neutrons and mesons. The energy of the gluon fields was trapped inside these new particles, giving them mass. This transition from free quarks to confined hadrons is called the QCD phase transition. It was the moment when most of the mass of the visible universe was created. Not from new particles appearing, but from the energy of the strong force being locked inside protons and neutrons by confinement. The mass of every star, every planet, every grain of dust, every living thing traces back to that moment when the cooling universe allowed confinement to take hold and transform the energy of the gluon field into the mass of matter. There's something almost paradoxical about this. The quarks are trapped. They can never be free. They exist in a permanent prison from which escape is impossible. And yet, their imprisonment is what gives the universe its substance. Without confinement, there would be no mass, or at least negligibly little mass. Without the prison, there would be no world to live in. The bars of the cage are the foundation of reality. Let me pull back now and put everything we've discussed tonight into perspective. We start with a simple question. Why can quarks never escape a proton? And the answer turned out to involve some of the deepest and most beautiful physics ever discovered. Quarks carry color charge. Gluons carry color charge themselves, which means they interact with each other, squeezing the gluon field into flux tubes that store energy proportional to their length. When enough energy accumulates, the tube breaks, but the energy creates new quark-antiquark pairs that immediately form new confined particles. The universe will not allow a naked color charge to exist. Confinement is absolute. At the same time, at very short distances, the strong force becomes weak, a property called asymptotic freedom. This allows physicists to probe the inside of protons and see quarks behaving as nearly free particles. Deep inelastic scattering experiments have confirmed that protons contain point-like objects with exactly the properties predicted for quarks. Jets in particle accelerators confirm the hadronization process. Lattice QCD calculations confirm the flux tube structure. Every piece of evidence points to the same conclusion. Quarks are real, physical objects that are permanently confined by a force whose strength increases with distance. And perhaps most remarkably, this confinement is responsible for the mass of everything around you. More than 99% of the mass of ordinary matter comes from the energy of the strong force, not from the mass of the quarks themselves. You are made of confined energy. The world is built from imprisoned light. There is something deeply humbling about this picture. We think of ourselves as solid. We think of the world as made of stuff, of material, of substance. But at the deepest level, what we call matter is mostly empty space and energy. The atoms are mostly void. The nuclei at their centers are tiny. And even those nuclei derive almost all their mass not from anything we would recognize as substance, but from the energy of a force field held in place by the peculiar behavior of gluons. You are made of particles that can never be alone. Every quark in every proton in every atom in your body is permanently bound to other quarks by a force that refuses to let go. And the energy of that refusal, the energy of that unbreakable grip, is what gives you your weight, your presence, your physical reality. The strong force doesn't just hold matter together. It is matter in the most literal sense. Without it, the quarks in your body would have barely any mass at all. You would weigh less than 100th of what you weigh now. You would be a ghost, a wisp, almost nothing. But confinement ensures that this never happens. The gluons hold on. The flux tubes maintain their grip. The prison walls stand firm, and the energy of that confinement becomes the mass of the universe. Every kilogram, every gram, every ounce of ordinary matter in the cosmos. From the dust between the stars to the core of the densest neutron star, owes its mass to the same mechanism. Quarks, trapped forever by a force that grows stronger the harder they try to escape. Gluons, carrying the charge they respond to, creating a self-reinforcing cage that can never be broken. And energy, vast amounts of energy, stored in the fields between quarks, manifesting as the mass of everything we see and touch and are. The universe is built from prisoners, particles that cannot exist alone, particles that have never been free and never will be, particles whose very confinement creates the substance of reality. And the force that imprisons them is unlike any other force in nature. It is a force that punishes escape, a force that converts your resistance into the raw material for more prisons. A force that turns energy into matter and struggle into substance. The next time you hold something in your hand, anything at all, remember what it really is. It is not truly solid. It is not truly still. It is a churning storm of quarks and gluons, moving at nearly the speed of light, exchanging color charges billions of times per second, confined by flux tubes of unimaginable intensity, all within spaces far too small to see or even imagine. And the weight you feel, the heft of the object in your palm, that is the energy of confinement. That is the strong force refusing to let go. That is the deepest, most fundamental mechanism in the universe, doing what it has done since the first protons formed in the cooling fire of the Big Bang, nearly 14 billion years ago. Quarks cannot escape. They were never meant to. Their confinement is not a flaw in the design of the universe. It is the design. It is what makes matter massive. It is what makes atoms stable. It is what makes chemistry possible and biology possible and you possible. The strongest force in nature is also the most creative. By trapping quarks forever, it built a universe where stars could shine, where planets could form, where life could emerge, and where conscious minds could look at the world around them and wonder what it's all made of. Now you know. It's made of quarks that can never escape, and the energy of their eternal confinement is the substance of everything.